Let's take a look at more interference phenomena. And we're going to start out with single slit interference, which at first sounds a little ridiculous. If we have a single slit, that's a single source. How can it have interference? What's it going to interfere with? Well, here's the idea. Imagine we have this single slit of width b. We can picture this as being made up of many, many small slits that are just not separated by anything. Seems a little weird, but it works. If we do that, we can then think about all of these slits as coming in pairs that are a distance b over 2 apart. Okay, seems a little silly, but bear with me. Now I'm going to imagine a screen over here, just like we did with two slit interference. We're going to do this with single slit. There's a screen. Now imagine a point on the screen right here. This point on the screen, I can draw a path to two of the dots, two of the points that are a distance b over 2 apart, two of the imaginary tiny slits that are a distance b over 2 apart. Okay, now I'm going to also define this angle theta. So theta is the angle from this straight line going across from the slit to the screen to this line that goes over to the point that we're interested in on the screen. Okay, so we will get a dark spot here if it's destructive interference, and we'll get that if the path difference is equal to n plus 1/2 times lambda. That's our condition for destructive interference, remember. And if we get one pair to get destructive interference there, my argument is all of these pairs from the slit will have destructive interference at that point, and on the screen we'll get a dark spot. Now, where is that angle? What is this theta? Okay, let's zoom in on the aperture. If we do that, okay, here's our 2 points that are a distance b over 2 apart, and I'm going to draw the two rays that go from those 2 points to a point on the screen, and I'm going to argue that those two rays are approximately parallel. Now I realize they're not actually parallel. They do intersect at the screen, that's kind of the point, but they're approximately parallel if the distance from the slits, or excuse me, from the slit to the screen is much greater than the width of the aperture. Okay, so bear with me. We're going to approximate them as parallel. Here's our angle theta, and I'm going to draw an additional line right here. This line is perpendicular to the two rays, and if I do that, here's our angle theta again. And furthermore, this right here, this little distance, is the path difference. Okay, look right here. That's a triangle, and furthermore, it's a right triangle. So I'm going to write in the sine of theta is equal to the path difference divided by b over 2, right? Sine is opposite over hypotenuse. Opposite the angle is the path difference, and the hypotenuse is b over 2. Now remember, we will get destructive interference on the screen if the path difference is equal to n plus 1/2 times lambda. So the first dark spot, the closest dark spot to the central maximum, will happen when n equals 0. Or in other words, when the path difference is equal to lambda over 2. So okay, sine of theta is equal to lambda over 2 divided by b over 2. That reduces to the sine of theta is equal to lambda over b. You can rearrange that. Lambda is equal to b sine theta. I'm going to make an approximation. If theta is small and measured in radians, then the sine of theta is approximately equal to theta. Now, maybe you don't believe me, but that's true. It can be proven in math. I'm not going to take the time to do that right now. But if we make that approximation, okay, if theta is small and measured in radians, then lambda is equal to b times theta, and theta then is equal to lambda over b. This equation tells us the angle that takes us to the first dark spot in a single slit diffraction pattern. So here's what the single slit diffraction pattern would look like. Okay, here's our screen, and I'm going to draw kind of a graph. So a big value in this graph is going to mean we get a bright, bright spot. So bright central maximum, here's our first dark spot at an angle of lambda over b, and there's a symmetric thing on the other side, and then successive dark spots are at multiples of lambda over b. So what we get is a bright, wide central maximum with dimmer, smaller fringes towards the outside. All right. Now let's move on to more about two-slit interference. And to do that, I'm going to draw the two-slit system right here, and here's our screen. I'm going to define this angle theta, similar to what we just did in single-slit interference. And what we're going to do is I'm going to zoom in on the two-slit situation again, like I did before. I'm again going to assume that these two rays that are going to the screen are parallel. Now I realize they're not. They intersect at the screen. But again, if the slit separation is very small compared to the distance to the screen, then this is an okay approximation. Okay, so if we do that, here's our angle theta, and I'm going to draw this helper line again. This is perpendicular to the two rays, and here's the path difference, and here's theta, and here is little d. So we will get constructive interference on the screen if the path difference is equal to n times lambda. We will get destructive interference if the path difference is equal to n plus 1/2 times lambda. Those are our old conditions for constructive and destructive interference. And if we look at this picture, the path difference in this situation is equal to, well, let's see, sine of theta is equal to the path difference divided by d, right? Opposite over hypotenuse. So the path difference is equal to d sine theta. So we will get constructive interference in this situation if n times lambda is equal to d sine theta. We will get destructive interference in this situation if n plus 1/2 times lambda is equal to d sine theta. Now, if this pattern is created on a screen, we would see something like this for two slits. Here we go. Now, imagine that we didn't have two slits. What if we had three slits, or five slits, or 10, or 20, or 100? Well, if we have many slits, we get a similar pattern, it turns out, except the bright spots become narrower. The dark regions become more prevalent, and the bright spots become narrower. So this d sine theta equals n times lambda, that still works. It tells us where the brightest peaks are, but the peaks become more like spikes. And eventually we get to something known as a diffraction grading. A diffraction grading is where you have many, many hundreds of slits instead of just two. You can say have 500 of these slits per millimeter. And in fact, they don't even call them slits anymore. When we get to that point, we call them lines. So you can get like 500 lines per millimeter. And if you do that, you get these big regions of darkness and these spikes of brightness. And what that looks like on a screen is you get little dots surrounded by darkness. Now, at this point, you might be thinking to yourself that this seems all kind of silly. What's the point? Well, one point is this is very useful for separating out different wavelengths of light. And remember, different wavelengths of light correspond to different colors. So let's say I send blue and red light through a double slit system. Okay, the blue and red light will have the same central maximum. But if you look at that equation, d sine theta is equal to n times lambda, we'll get different angles for different wavelengths. For the red will have its first peak right here. We'll have two bright spots right there, and then more bright spots right there. The blue, because it has a different wavelength, it will have different angles. The blue will have a central bright spot in the same place as red, but the first order maxima, that's what they're called, will be in different places than the red's first order maxima. And then same with the second order maxima. Now imagine we do the same thing with green. It would look like this. And now let's add in yellow. Yellow is between green and red, so it would look like this. Now add in purple. Purple slightly beyond blue, so it'd be right there. What about orange? Let's add in orange. Okay. What you're noticing, you get different colors in different places on the screen. You send in white light through the double slit aperture, and you get a rainbow on the screen. Okay. And not only is that pretty, it actually has some very important science applications that we'll talk about another time. Okay, so single slit interference and double slit interference. The dirty truth is that double slits are made up of two single slits. So because of that, shouldn't we get single slit interference from the two slits? And the answer is yes. So in reality, when you look at a true double slit interference pattern on a screen, we say that it is modulated by the single slit pattern. So here's a double slit pattern, okay, and here's a single slit pattern. In reality, what you would observe on a screen would be the combination of those two. It would look like this. Here's the single slit pattern, and the double slit pattern is, the word we use is modulated by the single slit pattern. This is what we would actually observe on a screen.